I hope you're all ready for a journey. Hey, what's up guys, my name is Cherno. Welcome back to another Hazel devlog. So as you guys know, over the last few weeks, I've been just battling all of the Vulkan issues because that's just my life now. Whilst I have fixed the majority of Vulkan crashes as far as I can tell, the design of the renderer itself is still not exactly where I'd want it. I mean, I don't think it's ever going to be where I'd want it. And unfortunately, there are still plenty of other issues. And I didn't really want to get to that stage before we solved the crashing, because the crashing is kind of the most important thing to solve in the beginning. But now that we can run without crashing properly across all GPUs as far as I can tell, we can move on to some of the more interesting problems, which is, why is everything so slow? I mean, isn't Vulkan supposed to be the fast API? So then why is the Vulkan renderer slower than the OpenGL renderer? Well, let's investigate. So the way that I do these devlogs, first of all, is retrospectively. So when I kind of say let's investigate, I've actually already done the investigation. I actually know all the answers. Well, all the answers I can know. So this is just really like a bit of a story time with Cherno, because I'm just telling you guys a story. And the story begins with hitting F5 and taking a look at the state of Hazel Dev. Okay, so let's take a look at how fast we can render a moderately complex scene in Hazel at the moment. Now, first of all, for all of you who were complaining that you can't see anything, I added a little bit of like a large font option here so that we can actually just increase the font. Let me just move this away for the purposes of recording these videos, kind of like a presentation mode, I guess. So hopefully you'll be able to see now. But anyway, I added this little performance thing. And the way that this works is it's very easy in our C++ code to just quickly add a macro basically with a name. In fact, I'll show you what that looks like if we hop into like wait and render as an example, right? So it's HZ scope perf. It's basically just the performance of a particular scope. It just starts a timer for the scope of whatever scope you write this code in. And the way that this is set up is that the name is kind of, I guess, unique for the frame. So this is like a frame-based timer. So in other words, if I call a function many times in the duration of like a single frame, it will actually accumulate all of the durations of that function in a given frame because it gets reset once per frame. So by using this, we basically have pretty decent CPU timings of how long each function takes. So just keep an eye on that. Let's go ahead and load like the sponsor scene. This is like a fairly decent scene. It's got about 1.1 million indices in it. So here's our sponsor scene. We're rendering it with like, you know, cascaded shadow maps. I mean, it's not the most complex thing. There are no real effects going on. And you can see the frame time, this is in release mode, is like 26 to sometimes 30 milliseconds. If I pause this for a second, 29.02 milliseconds, right? Now, let's take a look at these timers that I added. So things like update for rendering, this is called for every single material once per frame at the moment. 0.2 milliseconds, not too bad. Wait and render takes about 3 milliseconds. So that's the entire render command queue from the CPU side, right? So recording all of the Vulkan command buffers takes about 3 milliseconds. Not great, not terrible. Begin frame takes no time at all. Swap chain present takes 25 or so milliseconds. 24.15 that time, 24.4 that time. You get the point. It takes 24 milliseconds. Okay, so what's Vulkan swap chain present all about? Now, I don't have any GPU timers in Hazel at the moment. It's probably worth doing, but I've just been using profiling tools, so I haven't really like you know, felt like a huge need to actually add them. But I just want to make it clear that these are all obviously CPU timers. However, we can still use them to see how long the GPU takes, because the way that swap chain present works, at the moment the latest version of Hazel actually has three frames in flight at any given time. So we don't kind of render one frame at a time. We have up to three frames in flight. But for this example, I've set it back to one frame per flight. It's really easy. You can just set a number. So I've set it to one frame per one frame in flight at a time, so that we can basically sequentially see what's going on. So what this does then is basically submits everything to the GPU, all of our command buffers, all of our stuff. It gets submitted to the GPU, and then we wait. We have a fence that we wait on. There's one frame in flight, so we have to wait for that frame to finish before we begin the next frame. So after we submit that queue, we spend 25 milliseconds ultimately waiting. I mean, there's some like actual queue submission does actually take time. Presentation takes a little bit of time as well here. So VKQ submit will take some time, present will take some time. But then the fence waiting is the majority of this time. So 25 milliseconds, we're literally waiting for the GPU to finish its frame. So we know, even though we don't have GPU timers, And again, I can obviously bring this up and profile it in Nsight and see what the actual, what's actually going on and how long the GPU is taking. But just through this data, we can still see that the GPU it's clearly the GPU's fault, right? This is taking 25 milliseconds on the GPU basically, compared to about 3 milliseconds on the CPU. So why is the GPU taking so much time? And this is, by the way, this was like my last, I don't know, I don't want to say it was like 2 weeks because there were many other things I worked on, but over the last 3 or 4 days, this consumed me. I did not know what was wrong. And the thing is, like, problems like these, it's kind of easy to isolate in a way what's going on, but I still couldn't really solve it quickly. And I'll take you through that journey now. So basically my first step, and hopefully this will kind of help you guys, I try and give you an in-depth view at how I, figure out all these issues so that maybe you can apply it to your own projects. That's kind of my hope. But basically, where do we begin with a problem like this? Well, the first thing is you have to realize how your render is architected, right? In this case, it's very bare bones. There's basically no optimization at all. I'm pretty sure in this version, there's no backface culling, there's no frustum culling, there's no like draw sorting at all. So we have tons of overdraw. We have backfaces not being culled. And we are rendering the entire sponsor scene. I mean, we're not shading the entire sponsor scene because not all the pixels are in view, but we are rendering, we're submitting to Vulkan as a draw call the entire model, which is actually kind of good, right? I mean, if I had frustum culling, I'd probably turn it off because just to see, because that can kind of interfere with your results, right? I want to see how long the GPU takes in like a raw sense to actually render this entire mesh because that's what I care about. So, but we don't have any of that at the moment, so we don't need to deal with that. So my first concern was basically the complexity of the pixel shader, the fragment shader complexity, right? So is our fragment shader just too intense, right? Are we just doing too many calculations there? That coupled with the overdraw, which basically just means that like we might render something behind this blue curtain, and then we'll render the blue curtain in front of it. So in other words, we're calculating all the pixels behind this, and then that was a waste of time, turns out, because there's a curtain in front of it. So that's why usually you want to sort from like front to back so that you don't actually have so much overdraw. We're not doing that though, as I mentioned. So it could just be the pixel shader. Really easy way to check though is to just like try and make the area smaller, right? So let's zoom out. Now we're shading way less pixels, right? In fact, I could even just take that out, right? Or another strategy, I could just resize this and make it tiny. Note the time basically hasn't changed. I mean, it's changed a little bit. I know for a fact that fragment shader is not free, right? There's a lot of stuff going on there. We're doing soft shadows for multiple cascades. We're fading the cascades between each other. We're doing some pretty decent kind of stuff inside that fragment shader. But obviously, if we make this smaller, you can see it's still above 20 milliseconds. I mean, I guess present falls to maybe under 20 milliseconds, but it's still kind of significant. So ultimately, that's an easy way to just rule that out completely, but that wasn't enough for me. I was like, okay, let's stop doing all of the complex stuff in the fragment shader. I just want to see albedo only. Unfortunately, there's not really a UI thing for that. So if we go to the shader, we can basically set the output color of our main kind of forward pass to actually just be like mparams albedo, right? Like that. If I go back, we can recompile shaders on the fly. I open up the shader, hit reload. Good, but we're still at above 20 milliseconds, right? So that kind of confirms what I just showed you with the kind of fill rate by just making it less pixels, less calculations, less times we run through the fragment shader. So therefore, if it is the fragment shader's fault, you'd see a huge performance increase. You'd probably see the same here because we're just rendering as like albedo textures. We're still doing the texture lookups, but I mean, it doesn't really matter. We could set the color to something like, yeah, and obviously the shader will optimize out, this stuff, but we could ultimately just set it to like white or something like that. It's still like 20 milliseconds. Let's set it back to albedo just so we can actually see something, but you kind of get the point, right? It's not good. So what is going on here? Okay, well, the next stage, honestly, for me at least, I'm not saying this is the right way to go about this, but I was just playing around with things. I was like, okay, well, we are doing like a bunch of these shadow passes, right? This cascaded shadow map like situation, we're doing 4 we're basically rendering this 4 times. So let's go ahead and kind of just reduce the complexity of this, right? That's all we're trying to do, right? Those shadow passes shouldn't take that long, honestly, but I don't know. Let's try and reduce this as much as possible. Let's go to the shadow map pass. We know we're not doing it anymore. Now we're just doing geometry pass and the compositing pass. That's it. It's very, very simple. Right? One thing we could have done is also enabled hard shadows, by the way, because that significantly increases the performance, but whatever, doesn't matter. I tried that as well, probably. Okay, so back to sponsor. Probably just make it load on startup. But anyway, 6 to 7 milliseconds for this. I mean, yes, it's 1.1 million triangles. It's not trivial. We're not rendering a cube, but still, that's way too slow. So my next step was, okay, well, let's find out what's going on here. And the presentation takes about 4 milliseconds. This is a fast computer. Not the best. It's a 1080 Ti, the GPU here. Fast enough. Now, obviously, by the way, I didn't mention this at the beginning, but obviously I'm running in release mode with not full CPU side optimizations. Like I don't think I've enabled like, you know, any suitable inline function expansion, or like inlining, or like, you know, fast floating point instructions and like SSE2 and stuff. I don't know if I've got all that enabled, but it doesn't matter because we don't care about the CPU. But from the GPU side, aftermath is disabled and Vulkan validation is disabled. Vulkan validation usually significantly increases the CPU time. So I probably wouldn't have expected to see much of a GPU difference anyway. I'm not really sure what effect it has on the GPU, but usually it's kind of CPU side anyway. So it does have a huge effect on that. So that's all disabled, right? We're basically running as fast as possible here. Why is it taking so long? So next step was, let's profile this with Nvidia Nsight's frame profiler, right? So you can actually, I'll show you guys kind of how this works. You can actually configure it just through Nsight, which you can all, of course, download. You need like an Nvidia developer account, but that's free. You can get one of those, just register. There's all these different like types that you can kind of start, you know, connect to process, launch your application, fill in the application executable, the working directory. That's usually enough. I don't really touch these flags much. But then there's this thing called frame profiler, right? So what that does is basically just profiles your GPU to see how fast things are running, right? And it can also profile shaders. So I did that. Now I couldn't do that on this computer because you need like a Turing GPU or higher for some reason if you're trying to profile frames in Vulkan. I don't know if it's DirectX 12 as well requires that, but Vulkan does. So you need basically like an RTX GPU. My laptop behind me has an RTX 2060, so I jumped on that and I looked at the frame profile. Now it's a little bit slower. It's 2060 mobile chip compared to like a desktop 1080 Ti. So the performance is different. This desktop is faster. So the frame times were a bit longer. But guys, that shadow map pass, each cascade, 6 milliseconds. 6 milliseconds to do a depth-only pass of this thing, right? And if we look at what is actually in there, I mean, I've disabled my depth passes, but you saw, like, it's a cascade. It is the full model. Usually, maybe not a cascade 0, but a cascade 1 is the full model. But 6 milliseconds? What on earth is going on? And the thing is, that fragment shader is the most simple. There is no fragment shader. There's no like, we're not even like, you know, looking at the alpha of a texture to see if we should discard those pixels from the depth buffer. No, this is the shader. I mean, we've got a little to do there. Maybe the comments, the slow part, right? But there's nothing going on here. Why? Why is it taking 6 milliseconds? That was my first hint, really. And in retrospect, that maybe should have triggered some idea. And I think now looking back on it, at this point, I definitely would have been like, I know what's going on. But I didn't at the time. Draw calls are slow. That's the impact, basically. I looked at each draw as well. You can look at each draw. And it was slow. Each draw call was like 0.1 millisecond. There's 300 and, I don't know, almost 400 draws in this scene, right? So what's going on? I had no idea, honestly. I think I looked at some other videos to maybe help me see what else Nsight might have to figure this out. I tried using, there's something called GPU View, which is like a Windows performance toolkit kind of. It looks at your entire system and you can kind of see what is going on the CPU, the GPU. Well, GPU View specifically is for the GPU stuff, and you can kind of see what's going on. It's across all applications, but you can isolate it to your application, capture like a few seconds and then see. I even tried that. I didn't really want to go too far into that. It's very complex and very annoying to kind of, see what's up. But then I stumbled upon another Nvidia thing. Another Nvidia thing, which is also in Nsight, by the name of GPU trace. Now, these two things are very similar, frame profiler, GPU trace, because GPU trace also tells you timings. Now, you'll note that it doesn't support the same APIs. OpenGL DirectX 11, not supported. We just have D3, D12, we have Vulkan. So this doesn't support everything. Also needs a Turing GPU, so I couldn't run it on the desktop, I had to run it on the laptop. But this thing, right? Profile and applications use of GPU resources using real-time capture of detailed metric data. This thing is way more detailed than frame profiler. And what I've done is I've actually run it behind me. It's still open there. I captured 3 frames using it over there, and I transferred the file here onto this computer so that I could actually show you guys what's up. So let's take a look at it. This is what I saw. Now this looks very daunting, and I'll be honest. If you're not like, if you have no idea how GPU architecture works, this is going to be very difficult to look at. I'm not going to even pretend to understand half of what's going on here, but I do understand a little bit, and with some Googling, you can also kind of find out. But these are my 3 frames, right? Now, what I did on that laptop to capture this, before I did that, is I isolated the problem again. I said, forget the shadow passes, the ridiculous shadow passes. Let's just worry about an albedo-only main kind of pass, which is kind of what you see here. That's what I did, and you can kind of see it in the corner. That's what the capture looks like. It looks very widescreen because it's on that like ultra wide monitor. But basically I did that. So you can see here, this is my submission. I think I probably only had 1 frame in flight, maybe. I don't remember. But anyway, we have our queue submission, we have our command buffer, we have our 396 draw calls, which took 6.21 milliseconds. Albedo only draw calls. 6.21 milliseconds. Very slow. So what did I notice here? Well, first of all, we're looking for huge numbers. Now we see a bunch of stuff going on here. We see a lot of stuff not being utilized much. But this kind of blue thing, this PCI throughput, seems through the roof. 94%. Now, for those of you who don't know, PCIe is kind of that's how we connect the graphics card to the motherboard. So that bus is how the GPU gets information. That's how it gets data. Through the motherboard from like CPU RAM, for example, goes through the PCIe bus, right? That much I knew. I don't know what PES plus VPC throughput is, but PCI, I know what that is. So that's good, right? But if I didn't know, I'd Google it. Because this is like clearly more important than this probably, right? We can see that the PCI throughput is very high. The other thing I noticed, so we have SM, which is streaming multiprocessors, again, a bit of like GPU architecture, which I'm not going to explain at the moment, and warps as well. Warps are basically like little units of execution. It's basically like, when we like render something and we have a fragment shader which dispatches like a bunch of like threads to actually calculate pixels, they're called warps, those kind of like units of execution. So warp can't launch, and it says PS warp can't launch, so pixel shader warp can't launch. 99.7%. And it's like that for like the whole, like the frame ends here, right? This is where the draw calls end. It's pretty much like that the entire duration. So clearly this is somehow just, it can't launch. Why? Why would a pixel shader warp not be able to launch? Maybe because it's waiting on like the vertex shader to finish, or it's waiting on something, right? Very suspicious, right? PCI bandwidth, another little red flag. Look how high that is. PCI write, PCI read. What's going on, right? Why is there so much stuff going on with the PCI bus? Now, the first thing I thought of is, am I like streaming these textures in every frame? Am I updating, like, I don't know, maybe there's a bug in my code where I'm actually like just re-uploading all of my textures every frame or something ridiculous like that. Right? Didn't really make sense to me because, I mean, if I reduce the color to white, it's not sampling any textures anymore, right? So then, why is it still taking so much time? So I had no idea why. I had no idea why this was happening. So I hit up a friend of mine. I worked with him at EA, and I sent him like a little screenshot of this, and I was like, do you have any idea why my PCI throughput might be so high? And you know what? He came back to me immediately and he said, "It sounds like your vertex and index buffers are being stored in system RAM." And that hit me like a ton of bricks. I was like, my vertex buffers on my CPU RAM? No. And I quickly opened up the code. I quickly went to vertexbuffer.cpp. And to my shock and horror, my memory usage was set to CPU only. Now, I swear it was not like that all the time, because I think this may have somehow happened because I was copying and pasting code from around the engine when I switched to using VMA, which is like the Vulkan memory allocator. It's basically like a memory allocator you can use on top of Vulkan that actually like allocates memory and keeps track of it by itself, because you can only like provide 4096 allocations. But anyway, Vulkan memory allocation is an interesting topic. But anyway, I didn't always use VMA. I switched to it about a month ago. But ever since doing that, I guess like I had to refactor my code obviously for that. And I guess I somehow, I don't know, this must have just somehow slipped in. And index buffer is the same. That's OpenGL. Index buffer is the same, right? We have our CPU only. Well, I felt nice when I saw that. And the thing is, what's also interesting is that look at this poor excuse of a vertex buffer class. Because this was like one of those things, this is probably left over, minus the VMA stuff, from like Vulkan week, like a year ago or something. When I was like, okay, let's set this up, vertex buffers, let's just upload them, done. You know, we don't care about it. I didn't need to like dynamically update vertex buffers or like map the memory or do anything yet. None of that stuff, I guess, exists in the Vulkan implementation of Hazel Dev, at least. We don't really do any 2D rendering, I think. So this is just the way that it was, right? For whatever reason. I mean, there's no, like, we don't even have a destructor in this class. This was so abandoned. It was so old. So then when I saw this, I was like, well, this is a disaster. Let's change this. So you can't just change this to like GPU only. I mean, I will say that the G and the C, those two letters are suspiciously similar looking. They mean very different things. You can't change it to like GPU only without using staging buffers, which is like the correct solution. And now actually in the latest version of Hazel, I have switched this around to use staging buffers. But as a quick test, what I did, you can just do CPU to GPU, right? It'll upload it to the GPU. It'll be there. It's not gonna live in the CPU forever. Let's go ahead and switch that out for index buffers as well. Just that one little flag from CPU, or from CPU only to CPU to GPU, right? Let's go ahead and open Sponsor. And my gosh, look at that difference. 1 millisecond on present. That was a bad pause. 1 millisecond on present, down from like 4. Right? And again, we're not doing shadow passes. Let's go ahead and enable our shadow passes. And let's go ahead and we'll also change the shader around as well to not just be albedo. And just change that shader. Reload the shader. And there we go. And you can see that now, with this, in this view, we're down to like 9 to 10 milliseconds from like 22, right? And you can see our presentation. Now this is like, again, I've reduced it to just 1 frame in flight. So this CPU time, if I set it to like 3 again, it'll kind of get like, you know, it'll be happening at the same time. So we'd be even faster. But you can see that it's made a massive difference. Now there's still tons of overdraw, right? There's still lots of stuff going on that isn't ideal, but that one little thing, right? And after that, I think now the shadow map passes take like less than a millisecond each compared to like 6. It's scary. It's scary to think that enum, right, was set to the wrong value. That little piece of code was being set to like 1, just the number 1 instead of the number 2. And that little thing, that little flag just ruined everything. And to be honest, that's the scary thing with Vulkan. This would not have happened in OpenGL. I don't even know if it's possible to store your vertex and index buffer memory on your CPU RAM. Is that possible? I've never done it. I honestly don't know. But with Vulkan, it's so verbose, it's so detailed that I'm honestly scared at what else could be lurking in my code that I just missed. One little thing that just completely destroyed anything. And the thing is, like, I haven't run this through some kind of, like, I don't know if there's like Vulkan validators or some kind of, like, the validation layer obviously didn't say anything. It could have been like, hey man, your vertex buffer is like on your CPU RAM. That's probably not optimal. Because I know OpenGL, I think through the debug message callback, can give you like some hints or some warnings. Didn't see anything from Vulkan. I don't know, maybe I'm just doing errors only. Who knows? Maybe I'm a clown. I am a clown. But that's besides the point. It is really scary. And to be honest, I'm so happy that this is now running quickly. Oh, and sorry, one last thing. Now we can really see if it's the fill rate. I'll zoom out and oh, sorry, I forgot my little video mode. Look at that. 11 milliseconds, 4 milliseconds, right? So you can see now that now we are actually bound by that fragment shader. I can reduce this even more, right? It's about, well, now actually we're CPU bound. Look at that present, 0.9 milliseconds. That's doing all of the cascades, but it's taking about 1 millisecond. Now we're actually CPU bound, right? So yeah, that's life. You do one little thing and everything explodes. Nsight is fantastic, first of all, because how do you even find this stuff? Like, there would be no way for me to find this. I would have had to read all of my code. I would have never thought that the vertex buffer class was doing that, right? It just, maybe I'm not experienced with Vulkan enough. I mean, clearly not, but I just wouldn't have even thought to look there. But opening up GPU trace and then actually seeing that PCI throughput being through the roof, extremely, extremely valuable. But anyway, that was my week. So I hope you guys enjoyed this little devlog. I'm so happy that I've solved these performance issues because I was really worried about the performance of the Vulkan renderer in Hazel, because actually the OpenGL renderer was faster. No, it's not faster anymore, especially with multiple frames in flight in the Vulkan renderer, but it was like twice the speed. And now I know why. It's because in OpenGL land, I was storing my vertex and index buffers on the GPU. But in Vulkan, I was storing them on the CPU. And so as it's going through and drawing every piece of geometry, it needs access to that vertex buffer. Where does it get it from? Through the PCI bus from CPU RAM. And that is why it was slow. Anyway, hope you guys enjoyed this little devlog story time with Cherno. Let me know what you thought. Let me know if you had this problem before, you know? Let me know if maybe what I'm doing here is actually helping you, you know, kind of diagnose issues in your own engines, because that's kind of, you know, I mean, first and foremost, like it's obviously fun for me to show what I'm working on, and then it's fun for people to follow along, but I also, you know, hope that some of this is useful to the people who might be in the same position, because again, making engines is difficult, and yeah, like I think the community should be around to help each other as much as possible. But anyway, thanks for watching. Don't forget you can help support Hazel by going to patreon.com/thecherno. You'll get access to all of this source code. You'll be able to look at the Vulkan renderer in all of its quicker glory now. There's still a lot of work to do with that, but I think that I'm content enough to start moving on to some other features and not necessarily optimization, although that will come pretty soon. But a huge thank you to everyone who helps support on Patreon. That's why all of this is possible. Yeah, Devlog Monday. I'll see you next week.